Hello everyone, welcome back to CFD College. I'm Ashkan, and this is the sixth video of Fluid Mechanics 1 tutorials. In this video, I'm going to solve 3 problems about energy equation and using it to solve different problems and examples in Fluid Mechanics 1. I hope you enjoyed our previous videos. If so, please subscribe the channel. We have actually I have lots of videos about numerical simulation and CFD using ANSYS Fluent particularly, so you can enjoy them and you can learn CFD and numerical simulation if you want. Now let's jump to the tutorial problem. This is tutorial 6, and let's solve some problems. Problem number 109 of chapter 5. We have this system. We want to pump the water from this lake to this reservoir. A pump is to move water from a lake into a large pressurized tank. So we have a pressurized tank, and you know that it means that the pressure over this surface is equal to the air pressure, which is 2 atmosphere, as shown in the figure below, at a rate of 100 gallons in 10 minutes or less. So actually we know the flow rate. So Q equals 1,000 gallon in 10 minutes. Remember that. Not per minute, per 10 minutes. Will a pump that adds 3 horsepower to the water works for this purpose? Support your answer with appropriate calculations. Repeat the problem if the tank were pressurized to 3 atmosphere rather than 2. So first we want to solve this in situation that we have 2 atmospheres for the air pressure, and then with 3. As you know, since we have a fluid flow and we have a pump, and the friction is not negligible, it means that we have a loss, we should use energy equation. And first we need to find the key points. As you know, any free surface is a key point, so this is point 1 and this is point 2. Why? Because we have some info about pressure, elevation, and velocity. As you know, any free surface has velocity of 0, so both of these have 0 velocities. And we have a pump, and why did I choose 1 for this point and 2 for here? Because as I mentioned, we always need to follow the flow. So if we have water flow from this area to the tank, it means that here we have point 1 and here we should have point 2. Now we can write down energy equation between point 1 and 2. 1, 2, 2. So energy equation, P1 over gamma plus V1 square over 2G plus Z1 plus head of the pump. In energy equation, we always place head of the pump in the left hand side, and if we have any turbine we can put it on the right hand side, or we can place it on the left hand side but with a minus sign. So basically we have on the right hand side we have P2 over gamma plus V2 square over 2G plus Z2 plus head of the turbine and head loss, HL. What do we have and what do we know? In this system, we don't have a turbine, so this is 0. Pressure at point 1, it's a free surface, so P1 equals 0. And actually V1, because it's a free surface. If we place z-axis here, z1 is also 0. What about P2 or V2 and Z2? I mean the information about these parameters on point 2. P2 is equal to P air. So P2 equals P air. Here it's 2 atmospheres. V2 is 0. It's a free surface. And Z2 equals 20 feet. So what do we have? This is 0. Oh, sorry. This term is 0. This term is 0. This and this one. So what do we have in the end is HP equals P2 over gamma plus Z2 plus head loss. First, we need to find HP, head of the pump. It doesn't matter whether we have a turbine or pump. HP, head equals the W dot of the pump or turbine, here pump, divided by gamma Q. So the W dot is the net power. We have that 3 horsepower, free HP horsepower. We should convert it to pounds. So it should be multiplied by 550. Every 1 horsepower equals, let me increase the gap. Okay, now it's better. Every 1 horsepower equals 550 pounds per second. And gamma times Q in the denominator. Gamma equals 62.4 pounds per cubic feet times Q. So we need to find Q because we have the flow rate in gallons per minute. Just let me to find Q. First, Q equals 1,000 gallons per 10 minutes. So we know that every 1 cubic feet equals 7.48 gallons, and every 1 minute equals 60 seconds. So we have 0.223 cubic feet per second. Now we have Q, we can replace it. 0.223 cubic feet per second. So head of the pump equals 119 feet. Okay, now we have HP, P2, gamma, Z2. We can find the head loss. So from equation 1, we can find out that 119 feet equals P2, which is 2 atmosphere, and we need to convert it to pound per feet square. So P2 equals 2 atm. So P2 equals 2 times atmospheric pressure in PSI is 14.7 pounds per inch square times 144 inches square over feet square. So we have basically 4,230 pounds per feet square. Now we can replace it in energy equation. So HP equals P2, 4230 pounds per feet square divided by gamma, 62.4 pounds per cubic feet, plus Z2 plus HL. So from this you can find HL, which is 31.2 feet. It's positive. It's a positive value, which shows us this system will work. So the system can provide pressure equal to 2 atmospheres. But now in second, actually part B, we should replace 3 atmospheres instead of 2. So first let's calculate P2. So this is part A, here is part B. P2 equals 3 atmospheres, so P2 equals, you can calculate it, it's similar to this one, it's equal to 6350 pounds per feet square. Now we can go to energy equation and put these values. So 119 feet should be equal to 6350 pounds per cubic feet divided by 62.4 pounds per cubic feet plus 20 feet, which is Z2 plus HL, and in this situation HL equals minus 3 feet, so it's negative, and it's not possible because head loss should be positive. This means that this pump cannot do the work we want. It needs power to overcome this 3 feet that we have, this minus 3 feet that we need. So part A can be done, the system will work, but for 3 atmospheres it can't work. We need a more powerful pump. Now let's move to the second question. Problem number 110. Water is pumped from the tank. So we have this tank and water is pumped from it. The head loss is known to be, so we know the head loss means that HL equals 1.2 V square over 2G. Be careful about the unit, where V is the average velocity in the pipe. So V is feet per second, which is squared, and we have gravity, feet per second square. So in total we have feet. So this term can be added and used in energy equation because it has the unit. According to the pump manufacturer, the relationship between the pump head and the flow rate is shown in this figure. So we know HP equals 20 minus 2000 Q square, where HP is in meters. So here it's in meters, and Q is in cubic meters per second. Determine the flow rate. It's easy. So first things first, we have this fluid flow. Since we have the fluid flow and the pump, we should use energy equation. First, we need to identify key points. This is a free surface, point 1, and we should follow the flow. Here is the outlet, so it's point 2. Why? Because we know something about the pressure, elevation, or velocity. Here we know pressure is atmospheric, and we have the elevation, and this is the free surface. We know pressure, velocity, and the elevation. So we have our key points. We can solve the problem. P energy equation, P1 over gamma plus V1 square over 2G plus Z1 plus head of the pump equals P2 over gamma plus V2 square over 2G plus Z2 plus HL, head loss, and we don't have any turbine. So now we should think about what we know. At point 1, which is a free surface, P1 equals 0, V1 equals 0, and if we put the z-axis here, Z1 equals 6 meters. What about P2? We know that pressure at point 2 equals 0 because it's atmospheric, and we know Z2 equals 0, but we don't know anything about the V, the velocity. The only thing is we know is V2 has a value and we don't know it. But we know something. We know that Q equals V2A2. So we have a relationship between Q and velocity. Let's see what we have. This is 0, this is 0, and this is 0, and this one. So we only have 4 terms, if I'm not mistaken. Z1 plus head of the pump equals V2 square over 2G plus HL, head loss. Okay. So Z1 is 6 meters plus head of the pump 20 minus 2000 Q square equals V2 square over 2G plus HL, which is 1.2 V2 over 2G, and we know velocity equals the velocity at the outlet at point 2 because the diameter of the pipe is constant. So velocity remains constant. The average velocity actually, not the velocity in local positions. So we have this, and we also and have this. So from this we know V2 equals Q over A2. So if we replace the values, we have here 26 meters minus 2000 Q square equals, let me move this to here. This is V2 and we don't know it, we don't need it, equals V2 square over 2G, which means that Q over A2 square over 2G plus 1.2 Q over A2 square over 2G. And we only have one unknown in this equation, which is Q, because we know and there is one here. We know gravity, area we can be found from this diameter. So we know A2 and gravity. 26 minus 2000 cube equals Q square over 2. Let me factor out this. Q square over 2G A2 square times 1 plus 1.2. Yes. And now we can solve it, because as you know, A2 equals pi d square over 4. Pi times d is 0.07 square over 4. So you know A2, you have the value, and the only unknown is Q. So you can find Q from this equation, and we also know gravity equals 9.81 meters per second square. So from that equation 1, you can find Q equals 0.052 cubic meters per second. This chapter is easy, as you can see, but you have to be careful about what you have and identifying the key points. This is the third problem. In the third problem 114, you can see a turbine. The turbine shown in the figure below develops 100 horsepower when the flow rate of water is 20 cubic feet per second. So we know the flow rate and we know the net power of the turbine. If all losses are negligible, it's important. It means that HL equals 0. There is no loss. Determine A, the elevation, H, B, pressure difference across the turbine, P3 minus P4, and C, the flow rate expected if the turbine were removed. So if there was no turbine, we should find the flow rate. Okay, now since we want to find the elevation first, this H, we should find the key points for this. We know here we have one key point, and it's first point. Why? Because this is the flow direction and this is the start point. To find the H, we should choose one of these points, points 3, points 4, or the outlet. But what do we know about these? It's only outlet that we know something about the pressure at least. We don't know pressure at point 3 or point 4, but we know pressure at point, for example here, the outlet, point 2, because it's atmosphere. We don't know velocity, I know, in any of these points, but at least at P2 we know the pressure, so it might be helpful. So part A, from point 1 to point 2, P1 over gamma P1 over gamma plus V1 square over 2G plus Z1. Do we have any other pump? No. So it's equal to P2 over gamma plus V2 square over 2G plus Z2 plus head of the turbine. We have a turbine here in between point 1 and point 2. And head loss, but head loss is negligible, so it's 0. Now think about what we know. Point A is a free surface, so P1 equals 0 and V1 also equals 0. If we put the axis here, Z1 equals H, which we want to find, and Z2 equals 0. And also P2 because it's atmosphere, but we don't know anything about V2. We know the flow rate, so we can find it. Flow rate is Q is 20 cubic feet per second. Q equals A2 V2. We know the diameter, so basically we can find the area and the velocity. V2 equals Q over A2 equals 20 cubic feet per second over A2 pi over 4 times D square. D is 12 inches. You have to divide it by 12 to get feet. So velocity can be found as 25.5 feet per second. Now we have V2. The only remained term is head of the pump. We can find it, as I mentioned, you can find head of the pump or turbine from the net power, W dot divided by gamma times Q. So W dot equals 100 horsepower. As you know, every 550 pounds per second equals 1 horsepower. Divided by gamma, it's water, so 62.4 pounds per cubic feet times Q, which is 20 cubic feet per second. So HT equals 44.1 feet. Now we can solve the problem. This is energy equation, equation 1. As we know so far, these terms are 0. And we only have 1, 2, 3 terms. So if we replace the values, to equation 1, Z1 H equals V2 square, which is 25.5 over feet per second square over 2 times 32.2 feet per second square plus 44.1 feet equals 54.1 feet. Now second part B, we should find the pressure difference across the turbine. It's easy now because it means that we already knew our key points, points 3 and point 4. So we should write down the energy equation between these points from point 3 towards point 4. P3 over gamma plus V3 square over 2G plus Z3, there is no pump in between, equals P4 over gamma plus V4 square over 2G plus Z4 plus head of the turbine. And there is no head loss. So what do we know from point 3 and point 4? We know that we are looking for P3 minus P4. So these pressures are not the problem. V3 and V4. Look at the diameter of the pipe, 12 inches, and before and after the turbine. So the diameter is equal in these at these points. It means that velocities are equal. So V3, so since D3 equals D4, V3 equals V4. So these terms are cancelled. And also they are at the same elevation. So Z3 equals Z4. So these terms are cancelled too. So what do we have? What are the remaining terms? P3 over gamma minus P4 over gamma equals head of the turbine. So P3 minus P4 equals gamma HT. So P3 minus P4 equals 62.4 pounds per cubic feet times HT, head of the turbine, 44.1 feet. So P3 minus P4 equals 2.75 pounds per feet square. And part C. So this is part 1, this is part B, and now part C. Part C is about the flow rate expected if the turbine were removed. So if there was no turbine, what was the flow rate? In that case, we need our key points again. This is definitely a key point, point 1, and point 2 is at the outlet because there is no turbine, so there is no point 3 and point 4. So again, P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2 plus HT plus HL. There is no turbine, there is no loss. So what do we know? At point 1, P1 is 0, V1 is 0, and we know Z1 equals H, and we calculated this 50 4.1 feet. Z2 equals 0. So this term is 0, and we all know also P2 is 0 because it's atmosphere. So these terms are gone, and what do we have is V2 square over 2G equals Z1. So V2 equals the square root of 2G times Z1. So V2 equals square root of 2 times 32.2 feet per second square times Z1, which is 54.1 feet. So V2 equals 59 feet per second. Now we have to determine the flow rate. Flow rate equals V2 A2. So Q equals 59 feet per second times pi over 4, 12 divided by 12 feet. So the flow rate equals 46.3 cubic feet per second if there was no turbine. So it's the end of this video. We solved 3 problems together. I hope you enjoyed it. I hope you learned something from me, and hope for the best, prepare for the worst always. So thank you for watching this video. If you have any question or problem, you can ask in the comment section below, and until the next video, bye bye. Oh, sorry, don't forget to share these videos with your friends and like the videos. Thank you. Goodbye.